Okay, so sorry about the glitch in the network. Um, Reviewing what we just said initially, what I was trying to say, or what we introduced initially, was number one is that covalent bonds are the bonds that are peculiar or popular in organic compounds, and these covalent bonds, there are two types that you can have. The first one is as a result of what we call end-to-end overlapping. That's the first one. So once you are considering a covalent bond, this is the first form of covalent bond you can get. And this end-to-end overlapping will lead to what we call sigma bond. While the second one in covalent bond is what we refer to as your parallel overlapping. Parallel overlapping basically leads to the formation of our pi bond. And I'm going to continue by explaining these things in details as I did initially. Now, for us to see what I'm doing, I'm going to have to increase this camera. Let me just increase it a little bit so that we'll see what I'm doing basically. Now, in end-to-end overlapping, someone mentioned or asked a question what it means, or when I say coaxial. When you say something is coaxial, along an axis is simply along a particular plane. Whenever there is a combination or bonding, remember I told you covalence means if he brings one, this one will bring one, equal sharing. Their sharing is, that's why they are held together or joint. Now, when you talk about coaxial bonding, you are looking at a bonding along a particular line or axis. An axis is a line. So when I say coaxial, I mean both of them are coexisting on a particular line. That is what I refer to as coaxial. So in end-to-end overlapping, you are dealing with a coaxial overlapping between an S and P. It could be between S and P, it could be between P and P, it could be between S and S. The one I'm doing now is S and P. S is spherical, P is figure 8 or double or dumbbell shape. So once you have an end, look at this is the head of this particular P orbital. This is the head of this S. Once it is head to head joining, this is what we refer to as end-to-end overlapping. Now, this end-to-end overlapping is occurring along an axis. It's like a straight line. So if you happen to use this as the straight line, this is like an axis. If you have a straight line along this plane, this is an axis, and this bonding occurs on that straight line. That's why we say that once you are dealing with end-to-end overlapping, it is a coaxial overlapping between an S and P, a P and P, or S and S orbital at their heads. Once the head is bonding with the head of this one, what you have is an end-to-end overlapping. Now, I now mentioned something that once you are dealing with an end-to-end overlapping, it leads to the formation of a strong bond. That strong bond is what we refer to as sigma bond. So between the two types of bonds that are formed in covalent bond, the strong one is sigma bond. So have that in mind. And there are many reasons why we would consider sigma bond as stronger. The first reason is this: in bonding covalently, once the electron is accumulated or dense at the axis, automatically you have a stronger bond formed. So anytime you have an accumulation of electrons on the axis, let's look at this diagram. My diagrams are usually a little bit horrible, but let's manage. If I have that this is an s orbital, and then it has an end-to-end overlapping with a p orbital. This is an electron from the p orbital. Now at this point, this is where the joining occurs. Now an axis is simply a straight line, you get, and this is the straight line. Once the electrons are accumulated on the axis or on that straight line, there is usually a stronger bond. That is why when you have end-to-end overlapping, so let's put that down. Number one is end-to-end, you can put this down, end-to-end overlapping occurs at the heads of orbitals. The second point about end-to-end is that it leads to the formation of sigma bonds. It leads to the formation of sigma bonds. The third point is that it can occur between S to S, it can occur between S to P, and can occur between P to P. So if I'm doing an end-to-end overlapping between S and S, I'll simply draw two circles. and then overlap the two circles, and then put my electrons and possibly put a block to show that. And that this now is what we refer to as S to S end-to-end overlapping. If I want to now represent S to P, what I'm going to do is I'll draw a spherical or a circle or a sphere, which is for S, and overlap a figure 8 or dumbbell shape, and then put an electron. What I just did is now S to P end-to-end overlapping. And then finally P to P, I simply bring overlap two figure 8 structures. This is a P orbital, this is a P orbital, and put the electrons. What this is referred to as is a P to P end-to-end overlapping. So the major points for end-to-end, it occurs on the heads of the orbital. Secondly, the type of bond that is formed, it forms is sigma bond. And then finally, it can occur between S and S, S and P and P. That is that about end-to-end overlapping. Now, the next one that we are going to consider, or the next type of covalent bond, is formed as a result of a parallel overlapping. Now, just as the term or the name is parallel, when you hear parallel, you're looking at side by side. So if we are to just increase this to make us see or what I'm doing, sorry. So once you are looking at a parallel overlapping, number one is that parallel overlapping only occurs between similar orbitals. That is to say, it can only occur, in fact, in carbon atoms, it can only occur between P and P. So have that in mind, that parallel or overlapping cannot occur between P and S. The only place it can occur is between P and P. So in that type of overlapping, you have that the overlapping will occur on the side. So notice where I am joining this electron. I am joining the electron on the side of the orbital. This is the side of the orbital, and I'm overlapping them at the side. Once you have this type of overlapping, what you refer to this thing as is parallel overlapping. Now, what is the beautiful thing about parallel overlapping? Parallel overlapping will lead to the type of bond we refer to as sigma bond, as pi bond. Once you are dealing with parallel overlapping, the type of bond you are going to form is what we call a pi bond. Okay, so let's look at that. So as I said, things to note about a parallel overlapping. So number one is that parallel overlapping occurs on the side. These are things I would like you to write down. Number one is that it occurs on the side of the orbitals. The second point about parallel overlapping, it leads to the formation of pi bonds. The symbol of pi is just like that of pi r squared in our normal mathematics. It leads to the formation of pi bonds, and pi bonds are weaker bonds. They are not as strong as your sigma bonds. They are weaker bonds. We'll get to understand this when we go into hybridization. And then finally is that they only occur between P to P orbitals of a carbon atom. Now, considering the parallel overlapping, as I said, you have a figure 8, and then you overlap another figure 8 on the side. What you simply did is parallel overlapping. Put the electron here, put the electron here. You have that. So if I have 8 and I draw another 8 such that it overlaps it, the type of bonding I have here is what is called parallel overlapping. Now, the axis is usually drawn at this point. Now, notice that the electrons are not concentrated on the axis. They are positioned at a particular angle to the axis. So if you have that this is an axis, it is parallel to the axis. That is why it is referred to as a parallel overlapping. Added to the fact that it occurs on the sides of these orbitals, basically. So unlike our head-to-head or end-to-end overlapping, if it is the end-to-end overlapping, you have something like this, where the electrons are shared or joined at the center or along this axis. This is what we refer to as end-to-end. While in this case, this is what we refer to as parallel overlapping. So you have that basically about the two of them. These are the major facts about this type of overlapping. If I have questions, or if you have questions, please you can send them across for whoever is watching. Okay, well, I'll have to move ahead. Now, having mentioned this, the next thing that I am going to get into after discussing or having mentioned the two types of covalent bonds that can exist is to get into why is it that covalent bonds or reactions occur slower in organic compounds. I noticed that as one of the questions. The simple reason reactions occur slower in organic compounds is because of the type of bonds they form. The bonds they form are stronger bonds and can hardly be broken, and because of that they hardly get involved in reactions. So just have that in mind, that once you are dealing with a covalent bond, you are dealing with a strong bond that is not easily broken. Hence, for reactions to occur, it will be harder for these things to occur. Now, having said this, we would have to move into the next aspect of the study, which is hybridization. Now, whenever you think about hybridization is quite simple. Initially, we drew or explained the configuration of a particular atom. Let's say, for instance, we are writing the electronic configuration of carbon. It's going to be 1s2, 2s2, and 2p2. Now, if we are putting this diagram, it's going to be 1, 2, 3, 4, 5, 6. But as we said in the last class, that one of the electrons in the s is actually transferred here. So we are going to have it to become 1s2, 2s1, and then 2p3. We have 2 electrons here. We have 1 electron here. And then we have 3 electrons here. 1, 2, 3. Now, so you find out that in this particular case now, you can actually bond or have a covalent bond here, 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 and here. So the question is, what do I now mean by hybridization? An illustration to help us understand this before I get into the definition is, take for instance, I have a particular table that is supposed to be carried by 4 people. And on this side of the table, you have a very muscular young man. On this side of the table, you have a very, I don't know if you can understand this, my diagram. These things I'm drawing are muscles. This is the head, this is the leg, and this is his hand. Then you have another muscular guy. This is his head, and then this is his hand. And then finally, on this side of the table, this guy's leg, they won't have. On this side of the table, you have one slim guy here. Now, if you look at this particular diagram of these 4 people, you will notice that if the 4 of them are to carry this table, because their strengths are not equal, you would have that there will be no balance for this particular system. Why did I have to say this? The whole concept of hybridization is to ensure that the energy of everybody involved in the bonding is equal. So the first thing you need to take note of in hybridization is that hybridization is a process or a mechanism to bring about equal energy levels. Before we come to an official definition, just have this in mind, that the reason for hybridization is to bring about equal energy level. And what is the principle behind it? Combine and share equally. So if we are to now look at the definition of hybridization, we can now say that hybridization is simply a mechanism which involves the combination. Sorry, let's put up so that we can all read that and see. Okay. Okay. Okay, so let's move ahead. As I was saying, hybridization is simply defined as a phenomenon which involves, or a mechanism that involves, the combination of different orbitals in the same energy level. Combination of different orbitals in the same energy level to bring about the production of the same number of orbitals with equal energies and the same shape. So the fact that you have that this s orbital, this particular s orbital is in number 2 and p orbital is in number 2, does not mean that their energy levels are the same thing. This one might have 3, this one has 4, this one has 4, this one has 4, or something like this. In the case of hybridization, what happens is you combine all of them. You now combine all of them and make it 3 plus 4 plus 4 plus 4. After your combination, this is supposed to sum to give us 12 plus 3, which is 15. You now divide it into the number and share it equally so that each person has the same energy. If you share it equally, this is supposed to be 3.5. 3.75. So each person now has 3.75. Each person now has 3.75. 3.75. Sorry, I'm writing 57. 75 and 3.75. So basically, in hybridization, it is simply the process of combining orbitals in the same energy level. Why did I bring up orbitals in the same energy level? It means that I cannot combine, the energy level here is 2 and 2 and 1. I cannot combine this 1s with this 2s. Why? Because this one is in a different energy level from this. So in hybridization, you are combining different orbitals in the same energy level to give the same number of orbitals that have equal energies and the same shape. So that is the whole principle behind hybridization. As I said, the main aim of hybridization is to bring about equal energy. And how do you do it? Combine all of them together and now share them equally. That is what you simply do in hybridization. Now, you will now come across the fact that there are different types of hybridization. You have your sp3 hybridization, you have your sp2 hybridization, and you have your sp hybridization. What does this thing simply mean? Let's look at this thing again. So looking at the orbital configuration, this is 1s2, 2 electrons. This is 2s1, 1 electron. And then this is 2p3, 3 electrons. 1, 2, 3. Whenever you are dealing with hybridization, you are simply combining orbitals. Now, remember, because I said hybridization is the combination. So in hybridization, let me put down a definition on the side. Hybridization. So is the combination of different orbitals of same energy level to give the same number of orbitals with equal energy and same shape. Okay, now that's the definition of hybridization. Now, the point about hybridization, number one, is that you will notice something. The emphasis here is that you must deal with the same energy level. And then once you are dealing with the same energy level, it will give the same number of orbitals and they will have equal energy and same shape. These are the points of emphasis, which means I cannot hybridize 1s and 2s. Why? Because 1, this is a different energy level, and 2 is a different energy level. So the only guys that can hybridize are s and p. In this case, that is 2s and 2p, because the two of them are in the same energy level. Now, what are these types of hybridization? In sp3 hybridization, it means I'm combining this s with 3 of the p's. That is all. Once I'm combining one of the s with 3 of the p's, what I just did is s and p3 hybridization. So basically, that is that. Yes, so I hope you are following. Those of you that are here so far, I hope it is clear. Hope this is understood. The hybridization part, hope it is clear. If you have questions, please ask your questions now. I'll just give 60 seconds because of the lagging to just get your questions. Okay, so yes, any question from anybody? Okay, it's clear. Umenazu praise, I presume you are okay. Okay, very good. So in sp3 hybridization, you have a combination of one of the s with 3 of the p's. Now, this is now going to lead us to something else. The implication is that once you are now dealing with sp2 hybridization, what will sp2 now become? It will mean that you are going to be combining one of the s with two of the p's. That's sp2. It simply means one s and two p's. So in sp2 hybridization, you have one of the s in the second. You remember they have to be the same energy level, and this is 2 and 2. That's why I can combine them. You have one of the s combined with two of the p's, and I have sp2 hybridization, which means if I am now to finally do sp3 hybridization, I am now going to sp hybridization, I meant to say. It will now simply be between one s and one of the p's, and this will give me sp hybridization. So to draw it so it will look or have and become more clearer to us, I will start with the first one. I have this orbital one, sorry, just to redraw and make it a little bit clearer to us. 1 1 1 1 1 2. This is 1s, 2s1, and 2p3. So if I am to do sp3, it means one of the s and three of the orbitals in the p subshell. Once you are doing this, this is what we refer to as sp3 hybridization. Okay, in the case of sp2, this is going to be 1s2, 2s1, 2p3. This is one block with two electrons, but because it is not in the same energy level as number 2, I cannot hybridize it. Then you have this guy, 1 2 3. It will now be 1 2 3. So you find out that in the case of sp2 hybridization, you have one of the s combined with two of the orbitals in the p subshell, and then finally you have your sp hybridization. In sp hybridization, it is 1 1 sp. Sp means 1s and 1p. It is 1s, 2s, and 2p. So 1 1 1 1. So remember, you can only hybridize it if they are in the same energy level. So when 1 combines with 1, it is s and p. One of s and one of p. And these are the three different forms of hybridization. Now, we are now going to get into an in-depth study to understand this thing. The first question I would like to ask from what I just illustrated is, if I am to ask you how many orbitals are hybridized in sp3 hybridization, can you please tell me how many orbitals are hybridized in sp3 hybridization? Yes, Omenazu, praise if you are here. How many orbitals are hybridized in sp hybridization? Okay, so if you are following what I just explained, you will notice that the number of orbitals that are hybridized in sp3 is 1 2 3 4. Hybridization is combination. So when I say hybridization, I mean you are combining things together. So in sp3 hybridization, I'm combining s and 3 p's. S, which is 1, plus 3 of the p's, which is 3, would give me 4 orbitals hybridized in total. So have that in mind, that the first thing you are noticing in sp3 is that I have 4 hybridized orbitals in sp3. If we now decide to consider sp2, in sp2 I combined one of the s with 2 p's, which means hybridized orbital will now be equals 3. In the case of sp, you notice it's 2. Now let's get into an in-depth description or understanding of this concept so that we'll take questions on hybridization and then move ahead. Now let's start with sp3 hybridization. sp3 hybridization. So if we are to define it, you could write that this is the form of hybridization in which one of the s orbitals in the second energy level, or the s orbital in the second energy level, is combined with 3 of the orbitals in the p, 3 of the p orbitals in the second energy level. So I take it again. sp3 hybridization is simply a hybridization which involves combination of the 2s orbital with 3 of the p orbitals in the second energy level. hybridization that occurs between 2s orbital with 3 of the orbitals of p subshell in the second energy level. So this is what we refer to as sp3 hybridization. So as I put up my diagram, you notice that you have this one, okay, no, just one. Here is 1, 2. This is 1s2, 2s1, 2p3. So 1, 1, 1. So you have this. This is what we refer to as sp3. Important things to note about sp3 hybridization. Number one is that there are 4 hybridized orbitals. There are 4 hybridized orbitals. Anytime you have a hybridized orbital, the type of bond the hybridized orbital forms is a sigma bond. So that's the second thing to note. Hybridized orbitals forms sigma bonds. Hybridized orbitals form sigma bonds. So which means we can also say that there are 4 sigma bonds. Now I would like to say something about this. The number of hybridized orbital that a particular substance can form actually determines the number of atoms it is bound to. It means that if I say that a carbon atom is sp3 hybridized, it means that it has 4 hybridized orbitals. Hence, it can bond to 4 different substances. You can have an element here, an element here, an element here, another element here. Once you have that this particular carbon atom is sp3 hybridized, how you will note or identify an sp3 hybridized carbon atom is by counting the number of atoms that surround it. Once the number of atoms that surround it are 4 in number, it indicates that there are 4 hybridized orbitals. So, having said that, the implication of this thing I just said is this. Next point to note is that number of hybridized orbitals determines the number of atoms attached to a carbon atom. Number of atoms attached to a carbon atom. So once you notice that there are 4 atoms in a particular or surrounding or attached to a carbon atom, once there are up to 4 atoms surrounding a particular carbon atom, the implication is that the form of hybridization that occurs is S and P3, making it up to 4. One of the S was combined with 3 of the P's, and all together you now have 4 hybridized orbitals. So just have that in mind. sp3, you have 4 hybridized orbitals, and those 4 hybridized orbitals will now form 4 sigma bonds. Remember, the type of bond that is formed by a hybridized orbital is referred to as a sigma bond, and that sigma bond is as a result of end-to-end overlapping. I hope this is clear. I have one student with me here, so yes, the student. Okay, sir, please, must the elements be in the... Okay, so Praise was asking if the elements must be in the excited state. Yes, before combination of carbon atoms occurs, the elements in most cases must always be in the excited state. Okay, yes. So the answer, Praise, to your question, must the elements be in the excited state before they are combining? Yes. Whenever carbon atom is combining, it must always be in the excited state before it starts to combine. So just have that in mind. That's that about carbon atoms. Okay. Energy level of the s orbital. Energy level of the s orbital that combines in hybridization is 2. If you notice, we have 2s orbital and 2p. Once you have them in the same energy level, it means that they have the ability to hybridize. What this means is that if I look at, or if you consider this particular one, if you consider this particular s orbital, now this s orbital cannot hybridize with this guy. Why? This is energy level 1, this one is energy level 2. For hybridization to occur, the two of them must be in the same energy level. I hope this is clear. If it is clear, please just indicate. I'm actually waiting for your response so that I can continue. Okay, so having said that, with this said, now if I'm now to ask you, how many sigma bonds will an sp2 hybridized orbital or carbon atom form? That's the question. So put your answer out. I said I have a question. The question is, how many sigma bonds? How many sigma bonds? How many sigma bonds will be formed in sp2? So put your answer out. How many sigma bonds will be formed in sp2? Remember, the number of sigma bonds is actually determined by the number of hybridized orbitals, and it's literally given there. So what do we think? Put your answers out. Okay. While we are doing that, I just want to ensure that. Okay. The number of sigma bonds that are formed also determine the number of carbon atoms that are formed. The number of sigma bonds formed or the number of hybridized orbitals will tell you the number of atoms that will be bound to carbon. So don't get that mixed up. Now, still talking about sp3 hybridized carbon atom. We've mentioned few points about them. The first point I mentioned is that you have one of the S combined with three of the P's. That is one, which leads to the formation of four hybridized orbital. And these four hybridized orbital will form four sigma bonds. And these four sigma bonds will bond or will be bound to four different atoms. So just have that in mind. Having mentioned this, the next important thing that you need to note about sp3 is the bond angle. The bond angle for sp3 hybridized carbon atoms, or the bonds between them, is 109.5 degrees. Now, some of your materials or textbooks might tell you 109.27 degrees or just 109. So just have that in mind, that it is within this range of 109 to 109.5. I don't think there's any text that will tell you more than 109.5. This is what we refer to as the bond angle. So what this thing is trying to tell us is that an sp3 hybridized carbon atom is not necessarily a 2D diagram. It's more like a 3D diagram. You have one here, you have one somewhere here, one somewhere here, and probably one behind. So you have something like this as the structure of an sp3. So why is this referred to as an sp3? Because it can bond to four different atoms. You have hydrogen, 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 hydrogen. The implication is, once you are able to count the number of atoms, you can know the hybridization. If it is 4 in this case, it means S is one of them, and then you count the remaining 1, 2, 3, which means this is going to be sp3. Okay, to help us understand this more, imagine I have this type of, this is formaldehyde. In formaldehyde now, what kind of hybridization are you suspecting in formaldehyde? Can somebody help me answer this question? Please, if you are still around, just answer the question. In formaldehyde, what type of hybridization is likely to be in formaldehyde? What type of hybridization is likely to be in formaldehyde? What type of hybridization are you likely to have in formaldehyde. Okay, so I'm just waiting for your answer so I can move on. What type of hybridization? Is it going to be sp2? Is it going to be sp3? Exactly, sp2. Why it is sp2 is once you count the number of atoms that surround a particular carbon atom, you can determine the hybridization. That's how to do it. So you have that one of them is S is one of them, obviously, and then you have P into how many places? P2, and that's that basically. So let's move ahead. So I've talked about the bond angle. The next thing I'm going to say about sp3 before I round it off and go to the next one is that in sp3 hybridization, the most popular aliphatic hydrocarbon in which all its carbon atoms are sp3 hybridized is alkane. So alkane is a hydrocarbon in which every carbon atom in it is hybridized. So once I'm dealing with any alkane, methane, butane, ethane. Okay, let's look at it now. Methane, for instance, is CH4. Ethane is C2H6. If you are to draw it structurally, this is not an exact structure. We're just trying to put up a representation. If you are to draw this thing now, notice something. Let's count the number of atoms that are bound to this guy. You have S, 1, 2, and 3, which means this carbon atom is sp3 hybridized. Why? It is combined with 4 different atoms, and that is what indicates the hybridization. If you count the number of atoms surrounding a carbon atom, 1, 2, 3, and 4, if it is 4, it's S and P3, which means 1 plus 3 of them equals 4. This guy is sp3 hybridized, this guy is sp3 hybridized, and that's that for sp3 hybridization. Now, moving into the next form of hybridization, which is sp2. I don't think I need to say much about this, but the first thing is that it is a form of hybridization between the 2s orbital and 2 of the orbitals of the p subshell in the second energy level. So which means that once I am dealing with sp2, putting down the configuration, as I said, whenever carbon is to combine, before it combines, it excites the electron. So it combines in this excited state. So you have 1, 2, 3. So you have this now. In sp2, one of the S has to combine only with 2 of the P's. So points to note about sp2. The first point is that you have 3 hybridized orbital. 3 hybridized orbital. And once you have a hybridized orbital, the type of bond formed by a hybridized orbital is a sigma bond. So which means you're going to have 3 sigma bonds. Remember that I said that the number of sigma bonds will tell you the number of atoms it's bound to. So which means it's going to be bound to 3 different atoms. So you have that as the major information. Now before we move ahead, this particular orbital here that is not hybridized is referred to as an unhybridized orbital. So which means that we can say that an sp2 hybridized carbon atom has 3 hybridized orbital and 1 unhybridized. So let's understand. We've understood things about hybridized orbital. The first thing we understood about hybridized orbital is that the hybridized orbital, number 1, will form a sigma bond. The second thing is that a hybridized orbital, or the number of hybridized orbital, will tell us the number of atoms that carbon atom will be attached to. That is why in sp2, the number of atoms that it will be attached to is 3, which means if you count the number of atoms attached to a carbon atom and you notice it is 3, the simple implication is that it is sp2 hybridization. Now let's come to this unhybridized orbital. What are the things we need to know about unhybridized orbital? The first thing is that once you have an unhybridized orbital, it forms the pi bond. Unhybridized orbital will form a pi bond. So if you are writing, please put this down. An unhybridized orbital will form the pi bond. And the number of unhybridized orbital will tell us the number of pi bonds that will be formed there. So in conclusion, if I am to ask, the question is now put to you now, how many pi bonds and how many sigma bonds will be formed in an sp2 hybridized orbital. You can put out your answer and I'll move ahead. So put out your answer quickly so I can move ahead. I guess Praise is still with us. Praise, you still there? Exactly. So you are going to have 3 sigma bonds and 1 pi bond. Okay, Onyekachi is also with us. You have 1 and 3. Exactly. 1 and 3 is 1 pi and 3 sigma. Okay, yeah, probably. Yeah, that's correct. Okay, moving ahead. Let's move ahead with that. Now, one thing about the pi bond, I said that earlier on, is that sigma bond is the stronger bond. Amongst the 2 covalent bonds that you have, sigma bond is the stronger one, pi bond is the weaker one. Sigma bond can stand alone, but pi bond can never stand alone. So let's consider this now. Illustration. If you have a carbon atom and it is sp2, it means that you have 3 independent sigma bonds. The 3 independent sigma bonds can be attached to 3 different atoms independently. However, a pi bond can never stand alone. It is always attached close to a sigma bond or parallel to a sigma bond. So you have that once you have this as the 3 sigma bonds, sigma, sigma, and sigma. I'll use sig. This particular bond that just came to attach itself to the sigma bond is a pi bond. Now, did you notice something? That once you have a pi bond, it leads to the formation of double bond. You will notice that between these 2 atoms now you have 2 bonds, which is double bond between carbon atoms in this case. Why? Because you have 1 sigma bond and 1 pi bond. I take it again. That once you have a pi bond can never exist independently. Pi bonds are not designed that way. The bonds that are required to exist independently are sigma bonds. So once you have bonds that are independently attached to atoms, these are referred to as sigma bonds. The pi bond will simply come and attach itself as an extra, and this is what we refer to as double bond now. So you find out that when you have 1 sigma bond and 1 pi bond, you have double bond, which means triple bond will be as a result of formation of 1 sigma bond and 2 pi bonds, which we are going to see. Do I have, or is there any question with respect to this? I hope you all are following. Is there any question? If there's any question, you ask. If none, we'll move ahead. Because after this, we're going to take 1 or 2 questions. That is practical questions that are related to what you guys are doing in school, basically. Okay, go ahead. Umeazu, you said yes, sir, is for a question now. Praise. What's the question? Okay, no question. Okay, no worries. Which means you are following. Okay, so let's move ahead. Onyekati Anyako, I hope you are also following. If there's any question, please ask. I want to resolve them before I move ahead. Okay, so I haven't seen that there's no question. We're going to just move ahead, basically. Yes. So back to the things to note about sp2. So let's take that again. sp2. Once you're dealing with sp2, number 1 thing I said you should note is that you have 3 sigma. The sigma bonds is indicated by the number of hybridized orbital. Okay, let's start with that. You have 3 hybridized orbital, 3 hybridized orbitals. How will you know? It's telling you the number that combined 1s and 2p, which means 1 and 2. 1 plus 2 is 3. The next one is it has 3 sigma bonds. And then finally, as much as you have 3 sigma bonds, it has 3 hybridized orbital. It has 3 hybridized orbital and 1 unhybridized. Then this one has 3 sigma bonds and 1 pi bond. Remember I told you a sigma bond is formed by hybridized orbital and a pi bond is formed by unhybridized orbital. So when you have 3 hybridized orbital and 1 unhybridized, it means you have 3 sigma bonds and 1 pi bond. Okay, then the next thing we also took note of is that you are now going to have 3 atoms attached to the carbon atom. So once you say that a carbon atom is sp2 hybridized, it means that the number of atoms that are attached to it is just 3, and basically that is that. Now, sp2 hybridization leads to the formation of double bond between atoms, and that double bond is made up of one sigma bond and one pi bond. I'm just putting out these things as bulletins so that you will see the direct points you need to take note of about these forms of hybridization. Now, the next thing we are going to get into is the bond angle. sp2 hybridized carbon atoms have a bond angle of 120 degrees. Once you have a bond angle of 120 degrees, basically, and that's exactly why once you notice sp2 hybridized carbon atom, they are usually drawn as planar structures or triangular structures. You get, each of these angles are 120 degrees. Sorry, did I say 120 degrees? 120, yes, 120 degrees, yes. So each of these angles are 120 degrees on each side. So once you have this 120, this 120, this 120. But remember that there must be at least a double bond existing because it is sp2. Remember, the double bond, I explained how it is formed. The pi bond always attaches itself to a sigma bond. A pi bond cannot stand alone, so it always attaches itself to a sigma bond between carbon atoms. So, and then I think the final thing I would like to say is that the hydrocarbon that actually has this hybridization is alkenes. So alkenes are popular with respect to sp2 hybridization. So there has to be at least 2 carbon atoms in an alkene that has an sp2 hybridization. Okay, having said that, I'll talk about the final one and would move ahead from hybridization into other things. What is the final form of hybridization? The final form of hybridization is sp hybridization. Now, sp hybridization involves the combination of the 2s orbital with one of the orbitals of the p subshell in the second energy level. So the point is that once I have 1s2, 2s1, and 2p3, putting down the blocks 1, 2, 1, 1, 2, 3. If I am performing a hybridization where I have 1 combined with 1, it is going to be 1s combined with 1p, and this is sp. Okay, having said this, I will now be throwing out the questions for you guys to respond. The first question I would like to ask is, how many hybridized orbitals do I have in sp hybridized carbon atom? Okay, so let's answer that quickly. How many hybridized orbitals do I have in sp hybridized carbon atom? Let's do that quickly. How many hybridized orbitals do we have in sp hybridized carbon atom? How many hybridized orbitals? How many hybridized orbitals? Yes, I'm waiting for your answers. Oh. Let's get these answers and move ahead. Okay, Onyekati Aniako, correct. It's 2. Exactly. Now, what if I am to ask? Okay, that's the first point. So we are going to put that down. Let's start writing our points down based on what we just know. Let's start putting the points down for sp. So in sp hybridized orbital, the first point is that there are 2 hybridized orbital. Still on that, how many unhybridized do we now have? Yes? How many unhybridized do we now have? Basically, you will notice that we are going to still have 2 unhybridized. Basically, so we have 2 hybridized orbital and 2 unhybridized orbital. 2 unhybridized. Okay, having said that, the next point to take note of is how many sigma bonds and how many pi bonds will be found in an sp carbon atom or an sp hybridized carbon atom. Yes, let's put out our answers. How many sigma bonds and how many pi bonds? how many sigma bonds and how many pi bonds. In your response, you're going to say, if it's 1 and 3, you write 1 sigma 3 pi, or 2 sigma, and so on and so forth. So indicate quickly so we can move ahead. How many sigma bonds and how many pi bonds do we have? How many sigma bonds and how many pi bonds do we have? Okay, still waiting for your answers so we can move ahead. Okay, yes. Omenazu, praise God, that's correct. You have 2 sigma bonds and 2 pi bonds. Correct. Okay, so going back to our point boards, so which implies that you have 2 sigma and 2 pi bonds. Now, having mentioned this, the next thing we are going to understand or take note of is the number of sigma bonds is what indicates the number of atoms. So how many atoms are we going to have combined in sp hybridized? We'll have 2 atoms joined to an sp hybridized carbon atom. Let me even put it down here. Note, number of sigma bonds determines number of atoms joined to a carbon atom. So once you have that there are 2 sigma bonds, it means that there will be 2 atoms joined, basically. So you have that in sp, that only 2 atoms will be there. Now remember that these 2 pi bonds, imagine you have a carbon atom. We said it's only 2 sigma bonds you will have. These 2 pi bonds will come and attach themselves here, basically. So they will attach themselves to a sigma bond and lead to the formation of what we call a triple bond. So which means sp hybridized carbon atoms lead to formation of triple bond. So sp carbon forms triple bond. So you all should please take note of these important points. 2 hybridized and 2 unhybridized, 2 sigma and 2 pi. It will be bound to 2 atoms only. And because of the 2 pi bonds will be attached to 1 sigma bond, the number of bonds you are going to have here will now be equals triple bond. So anytime you have triple bond existing between atoms, it is as a result of what type of hybridization? Sp hybridization. Why? Because after sp hybridization, one of the sigma bonds, remember, 2 sigma bonds cannot join together. It's not possible. Whenever you see multiple bonds, one of them is a sigma bond, the rest are pi bonds. That's how it works. So in triple bond, 1 sigma bond and 2 pi bonds, basically. So that's that basically about your sp. The final point I would like to say before I move ahead of sp, okay, 2 more points, is that the bond angle in sp hybridization is 180 degrees. So let's put that down somewhere. We can put it down here. 180 degrees is the bond angle. And because of that, sp hybridized carbon atoms would have a linear shape. So basically, these are the major points about an sp hybridized carbon atoms. Having mentioned all these things, let's try out this question. Where is the question? Let me try to get okay. So let's look at this question, for instance. Okay. So the question is, what type of hybridization is found in acetonitrile? Okay, let me start by explaining what acetonitrile is. We are still going to discuss that. Whenever you hear the term acet in organic chemistry, acet implies 2 carbon atoms. I take it again. Acet, this is like the old form of naming or old system of naming. We're still going to discuss naming. The next class we're going to have is going to be strictly on naming. So we'll introduce hydrocarbons and then get into naming properly, basically, so that we'll start getting used to these names in time. So as I was saying, that whenever you are dealing with the old name, acet indicates 2. So when you hear acetonitrile, the nitrile bond is a bond formed where you have carbon joined by a triple bond to nitrogen. This is what we refer to as nitrile bond. So when it is now acetonitrile, it simply means that You have two carbon atoms, and one of the carbon atoms is attached to a nitrogen. Now, if I'm to eventually fill this up, we're going to have, remember, carbon can form 4 bonds. Hydrogen fills it up. Basically, we are going to discuss these things in details. So this is the structure of an acetonitrile. So the question is, what are the forms of hybridization that you have in your acetonitrile? Yes, let's answer the question quickly. And someone is asking acetone. We will get to that. I'll come to acetone. Let's discuss this one yet. I will come to acetone. I will answer this question you just brought up, but let's answer this one. What do we think? Yes, Onyekachi Anyako, what do you think? What are the hybridizations you can see here? Is it just one form of hybridization? Is it two? If it's two, what are they? If it's one, what is it? Okay. Anyaku says, I'm coming. My audio went off. Okay, yes. Your answer is correct. It is going to be sp3 and sp hybridization. That's to what's in they call them? Only Omenazu praise. I don't think I understand your this thing, but let me just explain it, Sha. Let me just explain it just to get. Let me take this thing out, the question out first. So we'll see it. Where is this question? Hybridization. Where are you? Shoot, where the question there? Okay, so let's take the question out so we can. Okay, use our full screen board. Now, to answer the question, acetonitrile. I told you acet simply means. Hey, what am I doing? Acet means two carbon. Then nitrile is now a triple bond between one of the carbon atoms and nitrogen. If I fill it with hydrogen, I'll have this. Now, to know the form of hybridization, all we needed to do is to count the number of atoms. In this particular carbon, you have 1, 2, 3, and 4 joined to this carbon, which means in the case of this carbon, you have sp3, because in sp3 is 4 atoms, s and 3 p's. That's why this carbon is sp3. Then if we now decide to check for this other guy now, this particular carbon is only bound to 1 and 2, which means the carbon atom that is only bound to just 2 atoms, it means that it only has 2 sigma bonds, and therefore you are going to have what type of hybridization? Sp. So this particular guy has sp3, while this particular guy has what? Sp. And that's correct, as we all said. Okay, let's try. We talked about acetone. Now, acetone is a different case anyway. How do I put it? As I said, acet simply means two carbon atoms, and then when the two carbon atoms is attached to a particular functional group, it can now determine the name of that functional group. In the case of acetone, it's like an exception. It's two carbon atoms that are attached to the functional group of an alkanone. The functional group of an alkanone is non-terminal carbonyl. We are going to discuss these things in details by our next class, or possibly if we have time, we'll do it today. But this is what we refer to as acetone. So putting down this diagram, you have 1, 2, 3. You have 1, 2, 3. We're going to discuss naming and structures in the next class, so don't bother yourself. Now, can you tell me the number or the forms of hybridization? Let me call this number 1, number 2, and then this is number 3. Now, what I want you to do is you tell me the forms of hybridization in each of these carbon atoms. So you tell me carbon number 1 has this hybridization, carbon number 2 has this hybridization, carbon number 3 has this hybridization. Let's do that quickly so we can move ahead of this particular aspect of the study. Oh yeah, Omelazu praise. I presume you understood my illustration or correction of the earlier question I gave. So yes, quickly let's do that and move ahead.